Hello, 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 hello. Okay, audio's working.
I didn't want to spend the time understanding something. That is that. Okay. Everyone. Hello. Oh yeah.
1:30.
Yeah, I mean, this area. So if we have questions about the lab, is there any other table? Do you have opportunity today?
Yeah. Monday, Wednesday, Friday, 3:30 to 5. Email is always an option. We have a lab TA. Help is, what we're all about. There's no lab today, but I'm the man. Okay, come talk to me. My office is on the 3rd floor of the Yale building. It's basically go down to the elevator, take it up to the 3rd floor, and go straight out of the elevator into the 304 suite. My office is on the east wall, 304D. It's amazing. I'm actually all set up on Wimba before class starts. Miracles will never cease. We might actually be able to use all of class time as we do this business. Okay, let's get started. Anybody have any questions? I'm glad you all realized that the room has changed. Anybody go up to 401?
I went over to engineering 109, the men's restroom.
Yeah, we are not holding the class in engineering 109, which is the restroom. Okay. Tony.
Number 1, should we have like a reading schedule?
You should be reading chapters 1 and 2. I've been less concerned about the reading at this point and more concerned about let's get the lab done. So I have not given out specific reading assignments. We've got I'm going to be finishing off this set of notes today, and then I'll be plowing through another set of notes that also talks about Lab 1, and then the following lecture is the lecture on Chapter 2. And that'll be followed with a lecture on Chapter 3. Okay?
Also, you showed me before how to make a symbolic link in Cygwin.
How do you make a symbolic link in Cygwin?
So that when I
LN-S.
What?
LN space dash S.
Okay. That's right.
Okay. Brad.
Does the new line character work with FPRNF?
Does the new line character work with FPRNF, like \n? Yeah.
Because I've been doing it and I think it's all in one line. Like, is there any reason?
Sounds like it sounds like an invalid user IQ. \R is a \n is just part of a \n. \R is the line feed and not the carriage return, but a \n should work. Show me. I do it all the time. I will run a program today where we use \n and it'll work. Yeah.
You mentioned that you could actually execute a program in a make file.
Yes. You sent me mail about how do you actually run a program in a make file. Everything that's a rule is just an operating system command. It's just a command you would type in. So you just put the /FIFO main.exe and pass its parameters as a rule without inserting a carriage return before the previous, between it and the previous rule. You don't have to declare dependencies on it as well. It's a wise idea to do that unless all of the dependencies would be satisfied by running the previous rules. So if the previous rule creates FIFO main and that's all you need to run FIFO main, well, there's no reason to make a rule, or no reason to make a dependence.
Okay, I was a problem with that. I tried playing around with it, so I put the output file as a dependency, so I just use the input file as a dependency, it's going to create an output file. So it's giving me some error on my text, on my third argument, on the command line, on the first one, the output file.
Okay. So now that I've had the chance to mull this over a little bit about the whole \r/n thing, it might depend on how you configured your Cygwin. If your default is DOS-based text files versus Linux-based text or Unix-based text files. So I normally use default configuration as a Unix-based text file on my Linux or on my Cygwin configuration. So I haven't tried it out with a DOS-based text file configuration under Cygwin, so that might be a difference. That's the only thing I can think of. Okay.
I've got a question for everyone. Has anyone tried running Cygwin on Windows 7?
Anybody tried running Cygwin on Windows 7?
Okay.
So we are seeing a report that Cygwin under Windows 7 is working correctly. For Garrett, but not for poor Stephen. Other questions? Got him. What is it? So GDB is not running on your Cygwin. Did you install it? Sorry. Does it give you any particular error? You can show me in office hours. After class is bad for me, but yeah, you show me sometime today. Any other takers? No other takers. Okay, let me show you one little slick thing here. Not this one. Here's Blackboard. Here's assignments. Lab 1 is now posted. Yeah, it's not slick. It's darn slick. Okay. I'm glad you're all still here. I'm glad you're all still engaged in the class, but it's going to go fast and furious from here on out. Lab 0 is easy. Lab 1 is hard. Okay? So take that into perspective. If you are just completely struggling with Lab 0, holy cow, okay, you need to talk to me. I'm not saying bail now, I'm saying come and talk to me. Lab 0 is not necessarily intended to be a 10-minute lab. I know that you guys are rusty on programming. It's intended to shake off the rust. And because of the fact that you're rusty, it's going to take a few minutes to do. But if it's not a matter of rust, it's a matter of I don't have the background to do this, or I just don't understand it all. Even after you've put in some time to get the rust out, we might have a problem. So if Lab 0 is giving you really, really big fits, come and talk to me. All right? Lab 1's a challenge. It's fun. It's interesting. We get our hands on boards. For the first time since I've taught this class, I'm going to let you work on pairs for Lab 1. So anyway, it's posted. It's up. It's good to go. I'm going to be talking about what we're doing with Lab 1 today. It might spill even into a little bit more next time, but you should have everything you need to get moving on it after I'm done talking today. Okay? All right. So last time we started talking about definition of embedded systems. We started talking about what are embedded systems, what's the difference between real-time, hard real-time, and soft real-time systems. And we started talking about how you do development for embedded systems. So this is what Lab 1 will introduce you to, is how we do this development. We have a host machine and a target machine. We have an interface between them. That interface is some sort of wire that lets us take programs that we develop on the host and put them on the target. Okay? There's some software infrastructure that has to be present on the host and the target in order to support this analogous compile, debug, run, execute, observe, modify the program loop that we typically do when we're writing software. So what the discussion for Lab 1 is going to be phrasing, what's the software infrastructure that we need to have available to us in order to do running programs, compiling programs, building them, and executing them, and so forth. Okay. So we need to have a host because we want to actually be able to see the code that we edit. We want to be able to make edits in a text editor. We need to have a target because that's where we're running the programs. Why can't we just test our programs on the host? Well, what language are we programming in? C. You have a C compiler for the host? You have a C compiler for the target? It's on Blackboard. So I'll talk about that one a little bit. But so if it's C and I've got a C compiler for my host, why don't I just compile my programs that I'm going to run on the target? Why don't I just compile and run them on the host? Anybody think that sounds like a good idea? I think it sounds like a fantastic idea. And you desperately want to do this every time it's possible to do. Okay? The reason why you typically can't do it is because embedded systems are computer-based systems which interact directly with their environment. Okay? Your host machine ain't set up to interact with its environment. Okay? If you're dealing with interrupts, with sensors, with low-level context switching code, your host machine can't hack that. Okay? Specifically, we're dealing with the loader code here, and we're going to be copying a program that we're loading into memory at an absolute address. If you try to touch an absolute address, you can't touch an absolute address on your host machine. You can only touch a virtual address. You can do some things to run and debug stuff on the host. The point that I'm trying to make here is try to use your host machine as much as you can because it's easier, it's simpler. You have a debugger here. You have all the development tools that you're familiar with. Over here on the target side, where you're doing cross-compilation, it just complicates life. Okay? There are times where you cannot execute any portion of your program that you're going to run on your target as a host program. Under those circumstances, all you have left is just build it for the target and run it on the target. But where you can and where you're able to, use your host as much as possible. Okay, so the build chain. Preprocess, compile, assemble. For each one of the files, we do a link, execute, print the output of the program, modify our source program. This is how we do development on a host. On the target, well, we don't edit source code on the target because it doesn't have a keyboard, it doesn't have a monitor. What we do is we use the host for doing the editing of the source code. We don't run a compiler on the target, we run the compiler on the host. But the program that we're compiling doesn't target the host, it targets the target. So we call that a cross-compiler. So we run these cross-compilation tools on the host, and that produces an executable file that we then feed through a loader program. That loader program actually has two sides of it, the host side and the target side, and we have this interface here. This interface is our wire that connects our host to our target. We execute it, and then we watch the LEDs blink. Okay? All right. So like I mentioned last time, RML GCC is the name of the cross-compiler that we will be using. It's a port of the GNU compiler collection, just the C compiler portion of it, to work on TS7200 boards, and it has no operating system support. Okay? This is the RML GCC version that I'm giving you. There are other RML GCC compilers out there that do depend on Linux or ECOS or some other real-time operating system being underneath them. Okay. Host side, target side loaders. The point of a loader is that you've got two computers. You've got your host computer and your target computer, and you've got to get them to talk to each other. What you're doing is you're taking an executable program that you're going to run on a target that you've built on the host, and you've got to get it from here to there. Okay? we've got to get it from here to there in some reliable fashion. How do we get it from here to there? There's lots of different ways, but specifically what we're going to be using is RS-232. Okay? So what do we need to do on the host side? On the host side, we're going to open up as a file the executable binary that we've cross-compiled. So this is going to be a file that is the output of our cross-build process that we've run on the host. We'll have that file, we'll open it up. The host loader is a separate program. It'll take that file as an input argument, and it'll open it up, and it's just a file that consists of bytes. Those bytes are the bytes that we're going to execute on the target, but we need to get it there first. So we open up the executable binary file on the host side. We open up a device handle for the interface, for RS-232. We've got to talk to Windows and say, please let me talk to the RS-232 port. And Windows will say, okay, I can do that. So, and I will provide you the code that does this, that talks to the serial port. All you have to do is just call a function that I provide you, and it'll download the code to the serial port. Okay? So you're going to open up a device handle for the RS-232, and then you're going to enter in a loop. And this loop says, for each packet in my executable file, send a packet and then wait. And we just loop until we send all of the packets. Then I'm going to send some done signal. Okay? So this is a 10,000-foot level view of what's going on the host. On the target, this is a program that runs at the same time that the host loader is running. The target side loader knows about the starting point address of where we're going to load the code. Now, how many of you all have ever worried about the address at where you're going to load your code when you're writing a host-based program before? You have to worry about where your program is going to run when you're running Hello World? Do you know what address it runs at? Does it run at the same address every time or different addresses every time? How many of y'all vote same? How many of y'all vote different? How many of y'all abhor democracy? You refuse to vote. What is this? Okay. How many of y'all vote you don't care? So actually, that one's the right answer. Simply because when you're running a program on your host computer, you don't have to care. That's a layer of the onion that we might as well just keep buried. We don't want to see that guy. Okay? We don't have to worry about what address we're running at. On a target machine with no operating system, you are not afforded such luxuries. Okay? So we have to be aware of what address we're going to start at. So by hook or by crook, we know what the address is. So we can either program the target side of the loader to already know that, or we can download it what the start address is, one way or the other. But by hook or by crook, we get the start address down on the target side of the loader. So then we just enter this loop that says, while there's still more data coming from the host, I'm going to do the following. I'm going to grab a packet 1 byte at a time from the serial port. I'm going to copy that packet 1 byte at a time to the start address, to the memory location pointed to by the start address pointer, and I'm going to increment the start address pointer. So I'm just copying the bytes that I receive into memory 1 byte at a time. Ka-chunk, 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 ka-chunk. Okay? So I just do this over and over and over again until I receive the done signal. As soon as I receive the done signal, then what I'm going to do is I'm going to execute a jump statement that jumps to the beginning address of the program. How many of all of you have ever written a program that you needed to jump to the beginning point of the program? How did you do that? What did you do? To where? What's the beginning of the program? An address? Did you jump to an address or did you jump to a label? Label? Okay. Yeah. So why'd y'all vote that you'd never done that before? A label in an assembly program is an address. You already know what address it is. You just called it a name instead of a number. Invalid user IQ. Okay. Those are the basic algorithms involved in the host side and the target side loader. Simple, straightforward. It's going to give you a little bit more fits than that. But that's just when your brain is out to lunch and you just can't understand what's going on in Lab 1, open up these notes and go back to this and think, okay, this really was what's going on. It's just a simple program, 2 programs running concurrently, one talking to the other. Okay, what do I mean by watch the LEDs blink? Well, we've got to figure out some output of the program. What is it doing? So all you have is LEDs and you have commands on your board that just blink LEDs, life becomes a little bit difficult. But if you think about it, if we have the ability to communicate packets through the RS-232, why don't we just use the RS-232 as a means of communicating output of our target side program back up to the host? Okay? So that's what we're doing. We have taken over, as a program runs, the RS-232 interface, and we can send bytes back up to the host, and those bytes can get printed to the screen. And all of a sudden, we've got something that looks very much like printf that you can execute on your target, and whammo, output appears on the host side screen. So it just looks like all of a sudden I'm running a program, and its output is scrolling to my screen. And gosh, that's starting to look kind of familiar, kind of like what I do on the host anyway. So we now have the ability, once we have the loaders in place, to do the compile, link, run, debug, visualize, modify, do it again, this whole development cycle. But now, let's suppose that you are an engineer working at an industry, and you've got to develop a new embedded system, and so you just get your hands on a new development board, and everybody's all excited because you get to start developing code. Well, we've got to have a loader. How do you get the loader onto your board? You've got a bootloader. How do you bootload your bootloader? Boy, this could go fun. What if it's already got a bootloader? Well, how'd they get the bootloader's bootloader onto there? Did they bootload the bootloader's bootloader? Okay. But you have this problem of getting the target bootloader onto the target. Does the target bootloader understand the .elf format? What's this .elf format business? Okay, so what's a .exe? Okay, what's the file format of an exe? How do you find out the file format of an executable? Okay. Here's p.c. This is a file that you're going to be running in Lab 1. Let's just build this sucker. gcc-o p.exe p.c /p.exe, just to show you there's nothing up my sleeve. That's a program that runs on the host. Great. File p.exe. MS-DOS executable PE for MS Windows console Intel 8386 32-bit. MS-DOS executable PE. That's the name of its file format. Okay. We come over here and run the cross compiler. It's good that I give the points and not get the points. Okay. T.elf, elf 32-bit LSB executable, targeting ARM. Okay. So T.elf is an executable file format targeting your ARM. P.exe is an executable file format targeting your host. Okay. They're both executable files, but if I come over here and I say /p.elf, okay. So I tried to run p.elf, and it says I can't execute a binary file. So I told it, give me execute permissions, just to show you I don't have anything up my sleeve. And it says, wait, I still don't know how to execute this guy. So this is not a matter of I don't have execute permissions. It's a matter of I don't know how to execute this. This executable file is a program that was built from p.c. We built it from the same p.c that we used to build p.exe, but it is an executable that targets the ARM. p.exe is an executable that targets the host. Okay? So we've got two different executables built with two different compilers targeting two different architectures. One we can run, one we cannot. So this ELF file format, p.elf is in the ELF file format. And it is a file format for specifying executable files. It's got all the instructions that we are going to use, the assembly instructions, as well as a bunch of metadata. So The question is, if we're going to use a bootloader program to load an executable that our cross-compiler produces, that bootloader had better understand the executable file format that we're going to download. Okay? The .exe format is not a binary snapshot of a program as it executes in memory. All right? When you load a program, when you say /p.exe, the operating system does some funky stuff. Okay? It loads the text section of your program into a certain chunk of memory. It loads the data section in another chunk of memory. It initializes the BSS section. So there's some stuff that happens at load time that you don't program. Okay? It's not part of your program, but it's stuff that operates on your program and prepares your executable in order to run. So there's this process of taking this p.exe file off of the disk and copying it into RAM. But there's some monkeying and some loading that goes on by the operating system beforehand because of the fact that this is in a particular file format. It has to be massaged in order to run it. Okay? That's what a loader does. You've never had to pay attention to loaders before because it doesn't really matter. If you have a binary dump of a set of assembly instructions, then that guy is just a regular old sequence of operations that can be fed straight to your processor. You can jump to the first address and go. But most programs that we write aren't in such a format. So we have to have a loader that understands the file format of the executable that we're going to run. I'm giving you a bootloader for Lab 1, but the bootloader is built in the ELF format, but it does not load files that are stored in the ELF format. So we have to have a bootloader that loads files in the format that we have available to us. If it doesn't speak ELF format, how do we load it? How do we load the executable files that we're trying to load using our bootloader? So in answer to question number 1, how does the target bootloader get onto the target? Well, we bootload the bootloader. How do we bootload the bootloader? Well, we just leverage the fact that the board vendor has supplied a native bootloader called Redboot on the board. Okay? The board comes out of the box ready to boot to Linux. Okay? It has an image of Linux on its flash, and so what it'll do is it'll say, okay, it'll load its own bootloader, and it'll load a Linux image, and start the Linux image. What we have to do is interrupt that process of where it loads Linux and tell it, don't load Linux. I want you to load another bootloader. So Redboot will reside on there. We will download an image of a bootloader that I'm going to give you to the board, and then that bootloader image will allow us to load 5780 programs. Okay? So, and there's a step-by-step set of instructions in the lab write-up that tells you how to load the bootloader using the existing bootloader. Okay. We have 8 megabytes of flash memory on the board. In that flash memory, we have Redboot, we have VM Linux, which is the Linux image. Okay. Redboot is an open source bootloader that's based on the ECOS operating system. Okay. VM Linux is a port of the Linux kernel. It has Bash and some shell utilities, some device driver support. So these boards already have Linux on them. If you want to fiddle around with the Linux on the board, that's fine, but for all of our labs, we're not going to use the Linux that's on the board. Okay? All right. We have a 5780 bootloader. This is the source code of the 5780 bootloader. Okay, it does a bunch of declarations. These are all variables that are declared as global pointers that we initialize to various addresses that facilitate our configuration and use of the serial port. Main is right here. We have 2 helper functions defined down here at the bottom called getch and putch. Getch gets 1 byte from the serial port. Putch puts 1 byte from the serial port. Puts 1 byte to the serial port. Okay. So what this bootloader does, it does some serial port configuration shenanigans up here, put this into supervisor mode, then we put ch a \n, then we put ch a pound. That's a character that's sent up to the host to say, I'm ready to receive a program. Okay, after the put ch, I have these set of commands right here that get 1 byte at a time of a 4-byte word called location. Location will be the location of where I put the executable. I have another gathering of a 4-byte word. That 4-byte word will be entry point. This will be the address of where I'm going to jump to when I'm done loading the program. So location tells me where in memory on the target do I put the executable. Entry point tells me where do I jump to once that executable is loaded. This assumes that your entry point and the load location are different, which is a valid assumption for the executable files that we're running. Okay. So we have this function pointer variable that we set equal to entry point, casting it to fn, where fn is type def to be a function pointer type. I'll tell you about that stuff in a bit. Size equals get ch. Well, size, so this is how we initially download packets. We get a size byte from the serial port while size is greater than 0. If size, this is a bitwise AND, 0x80, we're going to get a value from the serial port using get ch. We say size and equals not 0x80. Okay? So if size is 0x80, then what we're going to do is use this while loop to copy a value into a location. Else, while size minus minus, bin location plus plus equals get ch. So this just says, while there's still data going, give me a byte and put it into the memory location, incrementing the memory location as I go. Okay? This, you're going to have to dig through and understand what exactly is going on there. Not that tough to do. This is you're going to have to understand. This is basically what my little algorithm that I told you about, where you just copy a byte at a time from the serial port into memory. That's what that does. Okay. After I get through that while loop, I get another size byte. If size is 0, I exit the while loop. If size is non-zero, I keep downloading stuff. This right here jumps to the entry point. Okay? That's a 9,000 foot level, real fast view of bootloader.c. So that is what the target side of the bootloader does. We also have a host side of the bootloader, and I give you that code as well. But nevertheless, we have the bootloader. I have built a copy of that bootloader for you. I give you a .tgz file, a gzips tar file. You all know what a gzips tar file is, a TGZ? You know how to extract one? tar-xvzf, TGZ file name. Okay. Bootloader here, that archive contains bootloader.c and bootloader.elf. You can't build the bootloader. I'm not telling you how to build the bootloader. You can't modify the bootloader. You have to use my bootloader. Okay? This bootloader.elf is the executable that was built from the bootloader using the cross compiler and some funky switches that I'm not going to tell you about because I want you to use this executable. That way we guarantee that your compressor that you're going to write for this lab will work with the decompressor that's in this executable here. Okay. You're going to take bootloader.elf and load it onto a board. And then you're going to tell the flash, I want you by default to run bootloader.elf as the loader for this board. So that way, every time you, and then you'll write a configuration script that gets run by default so that when you power cycle the board, it'll run redboot, and redboot will run the 5780 bootloader, and that'll be the load cycle that happens all the time. So that way, your host side loader can run and download programs to the board. Okay, so this was in answer to how does the target bootloader get onto the target? Follow the steps in the lab write-up, and you'll load bootloader.elf onto the target and set up the configuration script so it will run every time by default. Okay, number 2, does the bootloader understand the file format output by the cross compiler? No, we can't just download an ELF file. Okay, we can download the bootloader.elf file because redboot understands ELF files. The 5780 bootloader that I'm giving you does not understand ELF files. It understands a file format called FLD. So we have our build chain. We take P.C that I showed you before, preprocess, compile, assemble. This is our cross-compiler format. So we take this through our build chain. We get 2 files, P.elf and P.map. So this is the executable file, P.elf. This is the program we want to run on our target. We want to load it using bootloader.elf, okay, that we're going to burn into the flash on the board. We also have P.map. P.map is a file that tells you that the linker tells you what it did with life and everything. Okay. So on the host side, as part of the build process, we take p.elf, and we're going to convert it into a new file format. This might seem a little bit involved, but it's necessary. Okay, so this is an executable file targeting the ARM, but sitting on the host file system. We run this through a tool called Object Copy, which converts the format of the ELF file into a bin file. This is like a snapshot of what the program will look like as it's resident in memory, preparing to run. Okay? So I told you that executable files have some metadata, meta instructions in them for doing initialization, for shuffling data around and so forth, some instructions that operate on your program, and those instructions you don't write, but the operating system does. Object Copy effectively runs the loader. So it will load p.elf into memory, and then what it'll do is it'll take a snapshot of the results of the loading process and put it into an output file called p.bin. Now, the tricky thing that's kind of weird is that Object Copy is a cross tool as well. So this is the loader that would run on an ARM processor in order to run natively an ELF file if you had an operating system to do this, okay? This all sounds kind of weird and funky, but that's just how this works. Okay, so p.elf, you run it through Object Copy, you get p.bin. p.bin is the image that you want to run of your program. This is the program, this guy we need to load. But we're going to change p.bin's file format a little bit by running it through a utility that I give you the source code for called bin to FLD. We also take p.elf and run it through readelf. This is a utility that's provided by the build chain that extracts the header information from the ELF file that tells you what's the entry point of this program, where should I load this program. That gets put into the p.config file. This is a text file. So this and this get sent through bin to FLD, and that outputs p.fld, which is the file format that our loaders understand. Okay? Once you have p.fld, you can send that to fld.exe, which is the host side of the loader that I haven't told you about. Okay. So that's how that's what you do on the host side to load a program. Now the question is, why on earth do we need all that? That's quite a mouthful. Yes and no. You don't always have to use the FLD format if you're developing a generic embedded system. There are reasons why we use it. I can go into the discussion of why we have it as we proceed in the semester, but I just want you to take it on faith at this point. Yes, you need it. Okay? Okay, how do I run a program on the board? So basically, I give you a make file that does all this stuff. Okay? All that you have to do is just type make p.fld on the command line on your host, and that'll take p.c and make the p.fld program. Okay? Then you say, or that'll make the FLD formatted of the p.elf executable file. Then you say make fld.exe. That builds the host side loader. Okay? Then you say /fld p.fld. This runs the host side loader, passing it p.fld, and so that will interact with the serial port and download it. Under the assumption that you have a board up with the 5780 loader on the flash and running, when you run fld.exe, passing it p.fld, there will be a synchronization between your board and the host side loader. The board will send up that pound sign. The host side loader will say, you sent me the pound sign. That means I can now start downloading packets. It'll take the packets out of the p.fld file, send them down to the target. The target will copy them into memory, and then it'll jump to their entry point, and the program, the p.fld program, will start to run on the target. Okay? And assuming that it's doing some output, you'll start to see output scrolling to your screen. Pretty easy, huh? Okay. What we're going to do next is dig through the gory details. I know that's just what you're all itching to do here. Yeah, so now the question is, what has this been so far if this hasn't been in gory details? We're just starting to scratch the surface. What do we talk about? Linkers? Okay, Garrett. Okay. Because of the fact that we have to, so the FLD program, so the question is, why are we using .exe? Linux doesn't need a .exe, but Cygwin does. The reason why is because Windows does. Okay? So when you build a program with GCC, by default, even if you tell it -op instead of -op.exe, it'll tack the exe onto the end. We have to use Windows because the source code for FLD.C, the source code FLD.C, which you build the host side loader from, is specific to Windows and has to be built with Visual Studio. But some slick stuff that I'm going to teach you how to do is how to use a makefile to run Visual Studio. That's cool. You don't appreciate how cool that is. It's just cool. It's good stuff. Okay. So, your host, your target, your interface, how do you build a program? How do you get it onto the board? Once you're there, how do you run it? We've got this chain here, p.c. We send it through this morass of cross-compiler, builder, whatever. We get p.elf. The elf file is just an executable file format, not just a sequence of instructions encoded in binary. So you don't think about the elf file as just, I've got my C file, I've translated it into assembly, and then I've encoded each one of the assembly instructions into binary, and that's all that's in the elf file. There's a lot of other stuff in the elf file as well, okay? And that other stuff tells the operating system how do you load this into memory in the right place, where do you initialize stuff. So, for example, put this group of bytes at address XXX, copy this data to YYY, zero out this section. We call it metadata because it's data that talks about your data. Okay? The loader must know how to deal with those instructions that are in the ELF file. The loader's job is to prepare the executable image for execution. It creates an image in memory. Once the image is created, it jumps to the entry point. The entry point is the address of the first instruction. Once you start at the address of the first instruction, you start executing the program sequentially until you hit a jump statement that causes you to jump. And anyway, the program just executes just like normal. Okay, what about cross-loading? So all this stuff applies to native loading, okay, where you're going to take an executable file and load it into memory. Cross-loading. Again, this is a little bit repeating what I was saying before. We've got the 5780 bootloader. It can't interpret ELF files, okay? What we want to be able to do is receive the executable image and copy it into memory. What we're going to do then is we're going to load the ELF file into memory on the host and then copy it down to a file format that we can then download, okay? We do native loading on a machine OS with ELF support. So if we had ELF support on the target, this is what it would look like. We send a.elf through a loader, and that would put it into RAM. So what's in RAM we refer to as the image of A, the image of the executable program. Cross-loading looks like this. Okay. P.elf, we have the image creation. That creates p.bin. Then we send that through the host side loader. Then through our interface here, RS-232, we have the target side loader, which then loads it into RAM. Okay. The stuff right here is on the target, on our board. The stuff right here is on our host. Okay, on the host side, we take the ELF file, we do the image creation, we create p.bin. This is the command to do that. We run arm elf object copy -r-f-o binary p.elf p.bin. Okay, -r says remove any sections in the executable file. -s says remove relocation and symbol information from the executable file. -o binary says when you're creating your copy of this object code, generate the binary image of the executable file. So you can use object copy to copy between all kinds of different file formats. But specifically what we're using it to do is to just generate a binary image of the executable as it would exist if it were being natively loaded. And then we take a snapshot of that into a bin file. Okay, now to take p.bin through the host side loader, through RS-232, send p.bin to the target as a sequence of bytes. The issue here is that p.bin can get to be pretty big, simply because what we're doing is we're taking an executable, loading it as an image into RAM, and then we're taking a snapshot of RAM and then sending that to a file. Okay, that p.bin file can be large for normal-sized programs. So what we want to do is address this issue. Why do we want to address it? Well, because we're using RS-232. RS-232 transfers data at a fixed rate. What that implies is that bigger bin files that we want to transfer, you get longer transmission times. So the whole idea, what we want to do for Lab 1 is reduce the transmission time, the transfer time when we're transferring data over the RS-232. So we're going to compress the bin file on the host, send it to the target, decompress it on the target, and run it. Okay? So this is the general format that we're going to run with. We take p.bin, we implement a lossless compression algorithm, we have this compressed p.bin file, we send that to the data transfer through RS-232. On the target side, we need to decompress, so the RS-232 signals come in, we receive the data, we uncompress it, we put it into RAM. So, there's an issue here. Whenever you implement compression, in order to save yourself some time, you can implement really complex compression algorithms, and what you end up with as a consequence is that the compression algorithm takes longer to run than the transfer time. So what we have to do is we have to balance how much complexity we put into our compressor decompressor so that we can actually save time during the compress, transfer, decompress cycle as compared to just sending the raw data. So we're going to define a simple file format that facilitates compression, just a simple run length encoding. Okay, so what we're going to do is we're going to transfer bytes in packets of up to 128 bytes in length. We'll have two types of packets, a compressed packet or an uncompressed packet. So what we do is we take the bin file, and we're going to just initially, without supplying any compression, we're going to take the bin file and chop it up into chunks of 128 bytes and call each one of those 128 bytes an uncompressed packet. We could then therefore just download that sequence of uncompressed packets and call it good. And that's what the initial tools do that I hand you out for Lab 1. And so when you have an uncompressed packet, the target side of the loader will receive that, detect that it's an uncompressed packet, and copy that packet byte by byte into RAM. A compressed packet represents a sequence of identical bytes. So if you had 7 threes right in a row, 7 bytes of threes all right in a row in your executable image, so 3, 3, 3, 3, 3, 3, 3, you could compress that into create a packet here that says 7, 3. So what that means is I've got 7 of the following bytes all right in a row. The byte value is 3. Okay? So instead of sending 7 bytes, I'm now sending 2. And if on the target side I say, if I can interpret the fact that this is a compressed packet, and I see it's got 7, 3 in it, then all I do is I just take this one byte that I've received from the serial port and copy it 7 times into the output. Okay? So that's how you do the decompression. So this tells you the number of repeated bytes. This is the byte value that's repeated. Yeah. The compressed packet will always be 2 bytes, yes. Okay, so I'm leaving it to you to study the bootloader.c program so that you can discern and discover exactly what the syntax of the compression is. So you've got to figure out what's the file format, the exact file format for specifying compressed packets and uncompressed packets. And the code that I showed you today is all the decompressor does. So that bootloader.c file contains all the information you need to decompress packets. Once you figure out how it decompresses the packets, you can figure out how to compress them. But basically the compression is just detect sequences of equivalent bytes. The compressor outputs a binary file. We're calling it .fld. It stands for fast load, which is then loaded by the PC loader. So end to end, we have what looks like this on the host side. You've got your cross-compilation process, which produces p.elf. Send that through object copy to produce p.bin. We send p.elf through readelf to produce p.cfg. Those 2 files are then fed to bin to FLD. Bin to FLD is your packetizer. It takes your bin file and creates the FLD file. That FLD file, p.fld, is then fed to your host side loader, FLD, which understands the FLD format, takes the data in p.fld, and downloads it through the serial port. Okay? So this is where you would implement your compression. Okay, in the bin to FLD file, where you're packetizing your input file. Okay, P.FLD also contains some header information pulled from the CFG file. The header information it contains is your load address and your entry point, because we don't necessarily know where we're supposed to load the program. We don't know where the entry point address is necessarily. So you have to tell the target side loader where those things are at. Okay. So the whole idea, implement data compression within this chain. What type of compression? It's called run length encoding, where all you're doing is figuring out a run of equivalent bytes and saying, okay, instead of sending each one of these individual bytes, all seven threes, I'm going to send a flag indicating that the following is compressed packet. I'm going to say how many bytes are in the compressed packet and what is the byte value that's compressed. So if you have a file that looks like 826664522 and so forth, your packetizer would go through and be scanning this whole sequence of bytes that is your executable file, and it would be looking for sequences of repeated bytes. When it finds a sequence of repeated bytes, it would say, I need to insert a compressed packet here. Well, the data before is kept in an uncompressed packet. This is kept in a compressed packet, and then the sequence of bytes that follows it may be compressed or may be uncompressed, depending on whether or not it's a sequence of equivalent bytes. Okay? So you just create the sequence of packets. Okay. This file format has the potential for significant compression if the data file has long sequences of repeated digits. One of your tasks in the lab is to figure out how good the compression is. So this is just an example that's highlighted here of what these packets would look like. So you'd have 282. The 282 would correspond to the fact that I've got an uncompressed packet that consists of 2 bytes, 8 and 2. So the 2 would be the size byte that you put on the packet first, followed by 8 and 2. This would be a compressed packet. So instead of sending 666, why would you want to send that? You'd send 36. Then followed by, assuming that the next 127 bytes are not compressible, I'd have an uncompressed packet that would be 127, followed by each of the individual bytes following that compressed packet. Yeah, Stephen.
The way you know that it's a compressed packet
is you're going to have to figure that out. You're going to have to figure out how do you know whether or not it's a compressed packet or not. You can't just assume that you always go compressed, uncompressed, compressed, uncompressed, compressed, uncompressed. But the bootloader has a way of discerning whether or not a packet's compressed or not. Just dig it out of the bootloader file. Okay. So next, what we're going to talk about starting next time is what I give you in the lab, and then we'll dig through the make file. Okay. So what are the files that I give you in the lab? We'll dig through the make file and figure out how does the make file do this building stuff that I've talked about. All right. TA will be in the lab tomorrow. Okay. Other deal is that forgot to pass these out. I've got these papers here that will allow you keycard access to Engineering 328. So I assume you know what these are. These have to be filled out and returned to Heidi. I have to sign each one. So if you want keycard access, please come and get a paper, fill it out, make me sign it.
What time is the lab?
The time is the lab. 10:30 to 4:30. Lab 1, you can work in pairs.
Yeah.
This is for getting keycard access to 328. Just put EC 5780.